So they sell pancakes by the stack, right? That sounds good. Right? Let's all go home and eat some pancakes.
You're hungry. You're talking about food.
I know. I've got burritos, tacos, pancakes for dessert. I'm sorry, guys. I'm kind of. I don't want to say I hate eating, but I like the idea of tasting food. I do chew my food, quite well when I eat because I like the taste. All right. So again, the two things that affect dispersion forces: size and shape. Okay, those two things affect dispersion forces. Here's some real data on size. You look at helium gas and on down through all the noble gases, and what do you notice about the molar mass? It gets bigger, of course. It went from neon or helium to xenon, and the boiling point also increases significantly as you get further down that column of the periodic table. So helium is still a gas, though, at room temp. Okay, and this because it's not polar, right? It's just an atom, right? There's no dipole attractions there. It's just dispersion only. Here's I was talking about distillation towers earlier with petroleum refineries. So here's your methane gas here. Methane boils at minus 162. It's definitely gas at room temp. And if you work your way down, obviously the molar mass gets bigger, and also the boiling point gets higher and higher. So do the melting points; they get higher and higher. And notice how the density also gets higher and higher in general. Okay. Which hydrocarbon would you say starts to become a liquid at room temperature? And the question then becomes, what is room temperature? What is that? So what would you say our degrees in Fahrenheit is right now, right here in the room? Maybe 70, 75 or something like that. Unless the thermostat's whacked out like it always is, then it's like 100 in here or it's 50. But usually it's around like 70, 75 degrees Fahrenheit. What would that be in degrees Celsius? Well, what is freezing in degrees Celsius? We know 32 degrees Fahrenheit is 0 degrees Celsius. Right, at 32 degrees Fahrenheit, we start to see ice form outside, right? And that's 0 degrees Celsius. So above 0 degrees Celsius, we have above freezing for water. Okay, these are water temps now. Our body temperature is about 37 degrees Celsius. So, and we run about 98 degrees Fahrenheit. So we know that room temperature is maybe somewhere around 25 degrees Celsius, right? So which hydrocarbon is going to start to condense into a liquid in this case? All right, boiling point, maybe pentane. Right? Pentane is a liquid at room temp, but butane is a gas at room temp, unless it's a really cold day, like up in North Dakota. Okay. All right, so right around this temperature is when we have butane be a liquid. Now, our gasoline is comprised mainly of pentane, hexane, heptane, octane, nonane, decane, C5 to C10. All right, it would really be unfortunate if we pumped gasoline into our cars and it just vaporized, before we could ever drive with it, So that's why we don't have, butane or propane or these lighter hydrocarbons in our cars unless we are running on a methane engine, okay? But if you're going to use methane gas as fuel, you have to really compress it so much so that it condenses into a gas. Okay, and that brings its own set of issues. So for the foreseeable future, we're still going to use regular gasoline. And they have to distill those stuff, right? I mean, we can't put, unfortunately, we cannot put these heavier hydrocarbons in our car because they're too heavy. Like the hydrocarbons do not have, they're too viscous, right? We cannot have moving cylinders unless we have a diesel engine, right? That's a whole different kind of thing. Okay, so this just shows the extent of the dispersion forces and how you can distill based on the boiling points. Here's just a graphical diagram showing the same thing. Nonane has 9 carbons, pentane only has 5. Molar mass gets higher, so does the boiling point. Now here's that's according to mass, size of the molecule. This is the shape issue. Here's N-pentane. N just means that it's straight across, 1, 2, 3, 4, right? Our line structure for pentane. Notice how the molar mass is the same between these two compounds. They're both 72.15 grams. They are structural isomers of each other. Okay, but neopentane has a much lower boiling point. Why is that? It's because of the shape, right? It's a round molecule. It's like trying to stack balls versus trying to stack pancakes. Here's your pancake, here's your ball, right? And so that decreased surface area between the between the neopentane molecules is going to diminish the boiling point. Okay. All right, so here's a quick question for you. Which substance in each pair has a higher boiling point? So between these two molecules, and they've been nice enough to draw Vesper sketches for us here, is this going to have a higher boiling point, or is this going to have a higher boiling point? One on the right, yeah. And why is that?
It's more elongated.
Yeah. Well, it's more elongated, but yeah, surface area, it's just bigger. It's got more electrons, right? And the more electrons you have, the more polarizability of the electron clouds you can have. All right, so the one on the right for sure. And then what about the pair down here, which will have the higher boiling point? More elongated, more round. But let me ask you this. These are kind of elongated, right? If they collide this way, sure, yeah, they got surface area. But what if they collide this way? Not as much. But what if I have a pancake now? Right? If I have two discs and I rotate the discs, it doesn't matter how they're rotated, they're still going to stick together. Right? Let's look at these two compounds. This is actually a 6-carbon ring, so it's almost like a pancake. Right? If I look at the 6 carbons in a plane. So it turns out that actually the one on the right will have the higher boiling point. And the reason why is because, yeah, this is elongated, but if it collides with another molecule like this, it might not collide exactly the right way to stick as much.
So because of the shape?
So because of the shape, right. So they're both flat. This is flat, but this is also flat, but it's a pancake. All right. This is like saying just a marker, right? It's flat in one direction, but it's not flat 360. So it's a lot easier to stack pancakes or stack plates than it is to stack markers, for example. Another way to look at it, like what if you're at Home Depot looking to buy some wood? You buy 2x4s, they stack but only so much, then they start to fall over. What if you're buying a whole sheet of wood? All right, that stays a lot more, right? It's got more surface area. So size and shape are what affect dispersion forces. God, I love it. Dispersion forces are great. All right. So any question about dispersion forces? All right. So what's the analogy I like to use? The mosh pit of chemistry. Dispersions, collisions, distorted electron clouds, irritable molecules, but they're not irritable forever. They're just irritable momentarily, and they stick. Okay. Do they even have mosh pits anymore?
Yes.
They still do? Okay, all right. Well, maybe occasionally there's still a rock band from the 90s that still puts on a show, but I don't know if you'd see a mosh pit at a Kendrick Lamar concert or something. Maybe out in the parking lot. I don't know. Anyway, okay, so I don't know. I miss the rock and roll from the 90s, we're going to tell you. It died from that time. All right. So dispersion forces are done. Now we're going to talk about dipole-dipole. So dipole-dipole molecules occur when you have two polar molecules that are now polar, permanently polar, and the negative end of the dipole attracts to the positive end of the other dipole of the neighboring molecule. Okay, so, and I left my model in my office. I'll have to show it to you upstairs. So, what creates polarity again? Like, how can we tell if a molecule is polar? For small molecules, we look at, it's one word, we look for asymmetry or symmetry. All right, symmetrical molecules are polar or non-polar? Non-polar. Asymmetrical means polar. Right. So if I had here's let's see, if we had a this molecule, which way would be the dipole moment? Yeah, kind of towards the chlorines, right? Right. What if he comes in contact with another dichloromethane molecule? So what a dipole-dipole interaction is when you have two polar molecules, the negative end lines up with the positive end of the other. Okay, and that's what a dipole-dipole attraction is. So this is not dispersion, all right? They're not necessarily colliding, they're just coming into contact with one another at the right angle, all right, or in the right direction. Okay, so remember what I said, all molecules have dispersion forces. So this is additive to the already existing dispersion forces there. Okay, and as a result, you'll have higher boiling points and melting points relative to molecules that are only dispersion force capable. Okay, so here's my best analogy for dipole-dipole forces. So if you look at this, does anybody here have dogs or any pets at home? And you ever take your dog for a walk, especially to the doggy park, you know, and you introduce your dog to other dogs, and what's the first thing they do? Smell each other's rear end. That's what they do. Okay. Molecules do the same thing. Polar molecules, I should say, do the same thing. All right. So here's this polar molecule. He's positive back here. He's negative right here. This dog on the wall is also positive right here and negative back over here. Okay. It's dogs smelling dogs or dog sniffing dogs. Okay. So here's an animation for that. I went back too much. Okay, so here's an animation for dipole-dipole forces. Here are all the dogs doing each other. Woof, 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 woof. You're all sniffing around, right? You know. All right. So repeat animation. Right. So all the negative ends and positive ends are coming together, but sometimes they do break off. They're not super strong, but they are somewhat strong. Alright, so you have to be polar to do this now, right? And since dogs have a head and tail, you can say polar molecules also have a head and a tail. Okay. So you have this directionality of the dipole-dipole interaction. If we take into account a polar versus non-polar molecule, here's ethane versus formaldehyde. The molar mass is about the same for all intents and purposes. So the dispersion forces in these two compounds are essentially equal, but one of them is polar, the other one's not polar. So this one would have a dipole moment. How? Which direction would the dipole moment point in this? Up towards the oxygen, right? Right. So if I drew a dipole-dipole interaction between formaldehyde molecules, it would be. Again, you have to draw the dipole arrow. All right, there's a dipole interaction between formaldehyde molecules. So as a result of that extra attraction, we have a very significant difference in the boiling point. Ethane boils off at negative 88, formaldehyde boils off at only minus 20, roughly speaking. So as you can see, definitely a significant difference. All right, same dispersion forces, but one's polar, one's not, and you get this huge difference in boiling points. Here's another example. You got propane, dimethyl ether. What do you notice about all these molar masses? 44, 46, 44, 44, 41. Okay, they're all about the same size, same dispersion forces, but look at the boiling points. The boiling points go up and up and up and up. Okay, why is that? Because you're looking at increasing polarity of the molecules. Right, propane is nonpolar. Dimethyl ether has an oxygen in the center. It's bent there, it creates a little bit of asymmetry. Ethylene oxide, a little more polar. See how that oxygen is pointing up even more now? Acetaldehyde, even a little more polar. Right, got this oxygen on one end and all carbon on the other. And then acetonitrile is even more polar. Okay, more asymmetrical, right? Symmetrical, increasing to asymmetrical, and you get a larger dipole moment and larger boiling point. Okay, which substance in each pair has the higher boiling point? So is it this guy or this guy with the higher boiling point? Second one, why is that? Yeah, more asymmetrical towards the right. So all these fluorine atoms are highly electronegative, so they're going to pull electron density from these guys, make it more polar than this. Okay, now if this comes into contact with another molecule just like it, the dipole-dipole attractions will be stronger. So don't forget, we're talking about interactions between two molecules now, intermolecular forces. Okay. What about these two? The cis will be a higher boiling point. It's more polar. Right? The trans compound there is nonpolar. Questions? All right. Away we go. So any questions on dipole-dipole forces? So okay, we have the mosh pit chemistry, and we have dogs sniffing dogs. All right. It may seem funny that I want you to remember those things, but remember that. All right, mosh and sniff. Okay. Make a new T-shirt brand out of that. Mosh and sniff. What? What are you talking about? I thought chemistry. Oh, okay. All right. The third force we'll talk about is called hydrogen bonding. Okay. Hydrogen bonding. Think about the octet rule for a second. What are the four atoms that need an octet? Carbon, nitrogen, oxygen, chlorine. CNOF, right? Well, if you take the C out of the NOF, you get the three atoms that, when bonded to hydrogen, can hydrogen bond. Okay, so if you remember CNOF and then just take out the C and just have the NOF, then you have the three different atoms when bonded to hydrogen that can hydrogen bond to other molecules. Okay, so what you're looking for are FH, OH, and NH bonds in molecules. Okay, what happens is that if you have one of those three bonds, so for example with, if I take a nitrogen, hydrogen molecule, this is a 3.0 electronegativity, this is only 2.1. So the electron density wants to go towards the nitrogen. Okay, now if it's bonded to, more molecule or more atoms in a larger molecule, here's my that works too. So if you have another bond here, you have more electronegativity going towards the nitrogen from this hydrogen. Right, it's got some lone pairs on there too, right? Remember, nitrogen always gets an octet. So these lone pairs are negative, and you get this extra negative charge coming towards it from the less electronegative hydrogens and also the carbon. So this extra negative charge on the nitrogen kind of creates a localized negative charge on there. Okay, and also you get this sort of localized positive charge on these hydrogens. And that creates negative, I almost want to say localized dipole moments, is what I like to call them. Okay, so the hydrogen atoms associated with the nitrogen, bond in nitrogen, is said to lack electron density. Right? So you'll have a slight positive charge on these hydrogens. And then you get this, and if you get it enough, you'll have neighboring molecules attracted. So H bonding, if I do it with water, water is the ultimate hydrogen bonder. Water is amazing, actually. Water is a really small molecule. It should be a gas, but it's actually liquid at room temp because it's got all of this hydrogen bonding that make the water molecules stick together. Okay, so let's make a comparison here. If I draw a dipole-dipole attraction between water, I get this. Alright, so here's a dipole-dipole attraction. Alright, if I do it with hydrogen bonding though, I can create a framework so the way they make hydrogen bonding is they do these little dots. Alright, the term hydrogen bond is a little bit misleading. It's not really a bond, it's just an association. Guilty by association, that's what they say. So this is a hydrogen bond, this is a hydrogen bond. Alright, all of these are hydrogen bonds. If I could ask you what's one main difference between H bonding and dipole-dipole forces, what would it be?
They're not really bonds.
They're not really bonds. Actually, well, dipole-dipole forces aren't really bonds either, right? So none of these forces are actual bonds, right? They're just associations, right? Dispersion forces is an association. What do I mean by an association? Well, I don't know. It's not a bond, right? It's just, you know, when things come into contact, they glom onto each other, but they're not really bonded. You know, it's like, I don't know. You're just kind of dating somebody, you're starting to see somebody, but you're not dating officially. You know the old, that's like, there's like a scenario, oh, they're seeing each other, but they're not dating. Alright, this is like, these are all situations where they're just kind of seeing each other, but they're not really dating per se, you know, officially. They're not an item yet. Like I told you, the intermolecular force is the dating game of chemistry. Okay, so they're not bonded yet, they're just sort of associated with each other. They're hanging out. So with that said, again, what's the difference between these two?
The bonds is a oxygen and hydrogen bonding, and then in the dipole it's just the chlorine.
So what you're alluding to is that there's, you know, you got the oxygen here with the oxygen there, whereas with this one you got the H and the oxygen, right? So I'll extend that a little bit further. That's the right idea. The difference between hydrogen bonding and dipole-dipole forces is the directionality. With dipole-dipole forces, you have to have the head lined up with the tail. Whereas with H bonding, you don't have to have the head lined up with the tail. You can just kind of do leg to leg and nose to head, right? All right, I don't have to take this water molecule and move it underneath here to get an attraction. Right? It's easier to have attractions when you can just sort of like take the molecule on its side and still have it interact with its neighbor. Right? Imagine what would happen to like the human population. Here we go again. Imagine what happened with the human population if people could only start dating if they faced each other face to face. Which is actually kind of a good thing, and it's probably better that way. But I'm just saying, how many times do you see people like check each other out? And it's like, do they stare at each other? Well, if they got any kind of social etiquette, probably not. Okay, or do they kind of just like do the glance? Right? You know what I'm saying? Hey, everybody, I'm checking you out. Hydrogen bonding is the nonchalant checkout. It's like, hey, okay. Whereas the dipole force is like, which is the stronger attraction? What do you find more attractive? Do you find someone staring at you more attractive? Or do you find someone who's just kind of like making it not known they're really checking you out more attractive? Probably the latter, right? So hydrogen bonding is a stronger intermolecular force relative to dipole forces because it's a numbers game. It's, oh, I can check out 10 different people at once, so I just line them. Versus if I'm staring at somebody, then you got other people and they're like, hey, that's not cool, you know? So, anyway. Do you get the idea? It's a directionality thing, and because we don't have to have the lining of the head with the tail, we don't have to have that directionality with hydrogen bonding. Because of that, we have more opportunities for attraction.
So the attraction between dogs and then humans.
Kind of, yeah. We're evolving here. It's called evolution. God. All right. So dogs have no social etiquette. They just, full on, like imagine like how you'd feel if somebody came up behind you, just sniffing your rear end. I'd be like, hey man, that's not, what are you doing? Oh, I'm sniffing you out. I'm doing some dipole attractions with you. Oh my God. Not a very strong attraction. He's like, do it. But then there's the hydrogen bonding where you got the more polished individual. Okay. Yeah. So that's the idea. It's a numbers game. You can have more hydrogen bonding interactions because of the lack of requirement of a direction to it. Okay, it's a numbers game. Okay. So and they kind of have, I don't know, if you go on Tinder or something, maybe there's some individuals that are really good at doing hydrogen bonding. They don't make it look like they're looking, but I don't know. So, oh gosh, yeah, forget I said Tinder. How do I know about Tinder? I'm married. No, I actually, no. I'll be honest. I had a student who told me about it. So, all right. No, so I used to have students write these biopics, and the student went into detail about their Tinder life. So. All right. Okay. They're like, hey, how do you know about Tinder? What's up with that? So, all right. Here's H bonding with HF molecules. This looks kind of like a dipole molecule interaction. But how would I draw this differently if I was doing a dipole interaction? All right, it would just be like this. All right, so we have HF. With the dipole interaction, we have to draw the dipole moment, right? And then we would have another HF. Right, versus, in this case, they're saying, oh yeah, here it's just HF with another HF. Right, so this would be the dipole case would be up here. And this would be the H bonding. So there's little nuances as to how they draw these, right? With H bonding, they just have the dot. Whereas with the dipole, they do the arrows, right? Just to show the permanent arrows. Okay. So if you have two molecules that are somewhat equally polar, but one can H bond and the other one can't, this is where you see the differences in the physical properties. Okay, let's see. Oh yeah, hydrogen bonds are pretty strong, but they're not nearly as strong as covalent bonds. So a typical hydrogen bond anywhere from 2 to 5% as strong as a actual covalent.